Okay, week 2, free response problem. So this is a 7-point problem, which means our suggested time is 13 minutes. So even before we read, I'm going to look at the picture, and I see that I have 2 blocks sliding down different ramps, and it looks like my tables are different heights, but my launch height is the same. Okay, but my starting height looks a little different, even though block 2 has a change in D. When it gets to this lowest point, it does pop back up, so I'll have to keep that in mind. Okay. So a physics class is asked to design a low friction slide that will launch a block horizontally from the top of a lab table. Team 1 and 2 assemble the slides as shown above and use identical blocks, 1 and 2 respectively. Both slides start at the same height D above the tabletop. However, Team 2's table is lower than Team 1's table. To compensate for the lower table, Team 2 constructs the right end of the slide to rise above the tabletop so that the block leaves the slide horizontally at the same height, H above the floor, as does Team 1 block. So it says both blocks are released from rest at the top of their respective slides. Do block 1 and block 2 land the same distance from their respective tables? Okay. So if I think about this problem, I see that I'm going down a hill, and that's pretty much a good sign that we're going to be conservation of energy. Okay. So my 2 positions that I'm going to want to look at initially is this first position where block 1 is, and then the position right at the end of the table. Same thing for block 2, this first position, and then the position right at the end of the table. Okay, so that's the first part. We have a conservation of energy part to begin with. From there, both of these blocks turn into a projectile problem, okay, where we have motion in the X and Y direction. Okay. This first question is asking about the distance from their respective tables. So that's going to be an X direction thing. Okay. So if we remember, in the X direction, okay, the only equation we can use is that X equals VT, because the acceleration in the X direction is 0. So if I look at the position versus time equation that's on my reference table, half AT squared, this initial X position we can assume is 0. Since acceleration is 0 in the X direction, because there's no net force in the X direction once we fly off that table, that can go away. So I'm left with X equals V0T. So it looks like what's going to determine this X position is the velocity at the edge of the table and the time. So let's think about where that time component comes from first. So the time component, remember, is dependent on the Y direction, or in a sense, the height that the table is, or how far the block has to fall. So in the Y direction, we're going to have an initial velocity of 0, an acceleration that equals g, meaning negative 9.8 meters a second squared. My change in y is the height. And again, we're going to use this y direction to find time. Okay? So looking at this list, it makes sense that the equation I should use is the position versus time equation. But because the initial velocity is 0, okay, that part goes away. My final position is the ground, or h. Or 0. My initial position is the height h, 1/2 gt squared. And remember, g is negative. So the time, 1/2 gt squared, is going to be dependent on the height. So if the changes in height off the edge of the table are the same, then the time is the same. So for both of these, h is the same. Okay, so my time in the y direction for block 2 would look exactly the same equation-wise as table 1. So that's good to know. So this time thing here is the same for both. Okay? So I'm just going to write myself a note. Time in air is the same. So the other thing that final distance in the x direction is going to depend upon is the velocity. Now, we're not going to use kinematics to figure out what the velocity is off the edge of the table. We're going to use energy conservation. Okay. So block 1 at this position here only has gravitational potential energy, okay, which is PEG or UG. Then for table 1, when we're at this very bottom spot here, we only have kinetic energy. So all of that initial potential energy is going to convert to kinetic energy. To make my life easier, I'm going to set this table height as 0. So my change in height here is really that change in distance. Okay. So all that initial potential converts to kinetic. Now for block 2, we again start with potential energy. Okay. And while block 2 does have a change in height of d, much like block 1, block 2 rises back up a little. So at this position here, we have kinetic energy and some potential energy because, again, I'm calling this tabletop height my 0 height. So if we're slightly above that tabletop height, we're going to have some potential energy. Okay. Now, both blocks start a distance d above their respective tabletops, which means both of these initial energy values are the same. Okay. So that would mean if they both ended at the table, they would have the same kinetic energy and have the same speed. However, block 2 does not fly off the table at the height of the table. It flies a little bit off the flight of the table, or the height of the table. So we have this potential energy component. So block 2 actually has less kinetic energy when it launches off the table. Now remember, kinetic energy is where we're getting this speed part from. So if block 2 has less kinetic energy, then that means block 2 has less speed, which means block 2, for the same amount of time in the air, is going to travel less distance. So that's how we're going to answer question A. There's a lot to get through just for one question. So, do they land the same distance? The answer is no. So justify your answers. So let's talk about what is the same first. So even though the blocks start with the same potential energy relative to the table, okay. And both blocks spend the same amount of time in the air off of the edge of the table. Because they have the same change in height off the table. They will not travel the same distance. Okay? And even though these things are same, like we said, the reason why they aren't the same is because of this difference in kinetic energy, which leads to a difference in speed. So that's going to be the next part of our answer. Let's actually say energy is conserved as both blocks travel down the ramp. Okay, if there's any physics principles that are involved in your problem, you should directly mention them by name. So energy is conserved as both blocks travel down the ramp. However, block 2 is launched at a higher height relative to the table. So block 2 has less kinetic energy and therefore less speed off of the table. Less horizontal speed means less horizontal distance. My handwriting got kind of bad there at the end. Sorry, my fingers are cramping. Hi. So that's question 1. Now I'm going to go over the scoring guide for question 1 real quick to see how I did. Okay. So I get no points for selecting no. Okay. A lot of the times with these questions, it's your explanation that is important, not the correct answer. So for attempting to use conservation of energy of the two to compare the two blocks, I definitely did that. Because I actually said energy is conserved as the blocks travel down the hills. For explicitly or implicitly, so implicitly means you imply that they have different launch velocities, or you explicitly say they have different launch velocities. I talked about having less kinetic energy and therefore less speed. Okay, so that I got that point. For stating or implying that the time to reach the ground is the same for both blocks, I definitely did that because I listed everything that was the same in the beginning. So I got all 3 points for this initial problem. Okay, now let's look at question B. So in another experiment, teams 1 and 2 use the tables as low friction slides with the same height. So they're at the same height. Okay, so just like before, we're going to have the same time of flight. Okay. But they have different shapes. So, and it looks like both my blocks are launched at the same height, which means they're going to have the same velocity off the edge of the ramp, okay, because my initial UG is going to convert completely to kinetic energy, which means they're going to have the same velocity because this initial potential energy is the same. Okay. I have no idea if that's going to help me with the answers, but it's nice to have notes written down that maybe I've figured out in the previous part of the problem, because maybe those things will help me figure out the other part of the problem. So both blocks are released from rest at a point of their respective slides at the same time. Which block, if either, lands farther from its respective table? So before they were asking, do they land at the same distance from the edge of the table, which we can call D. Now they're asking, how does that landing distance compare with these new tables? Well, if I have the same time of flight, okay, and the same velocity, remember we talked about before that x direction distance is dependent on the initial horizontal velocity and the time of flight. So if both of those things are the same, then that x position is going to be the same for both blocks. Okay, so this is going to be the two blocks land the same distance from their respective tables. Okay, so I'm going to write my brief explanation down here. Okay. All right. So both blocks start with the same potential energy relative to the tabletop. Energy is conserved, and both blocks, UG, converts completely to KE before launching off the table. So both blocks have the same KE and velocity at the edge of the table. The heights of the table are the same. So the time of flight is the same. So both blocks will travel the same horizontal distance. So it's a very similar explanation as part A, just this time they are the same. Okay, so let's check my answer. Let's make sure I've included everything I need to. So the correct answer is two blocks land the same distance. Awesome. For indicating that the change in potential energy from release to launch is the same, I did that. For indicating explicitly or implicitly that the launch velocities are the same, I did that. Okay. So now on to number 2 for this part B. Oop, that's part A. So part 2 says which block, if either, hits the floor first. Okay, well, we know the amount of time in the air off the edges of the table is going to be the same. So that part isn't going to really affect which one block hits the ground first. Okay, so we really need to figure out which block gets to the bottom of the ramp first. Now, a lot of you are probably able to intuitively think, oh, well, table 1, because it's steeper, right? So table 1 is going to get to the bottom faster. Okay, but we need to figure out a way to turn that into physics terms. So we need to think like energy conservation, but with energy conservation, remember, it's path independent and there's no really time tied into that. So not going to use energy conservation. So when we're trying to think about times, really what you should be thinking about is accelerations. Okay? So when you're trying to think about the time it takes to complete something, you want to think acceleration. Okay? And what do accelerations come from? They come from forces, right? So if we think about these as inclined planes, briefly, right? This inclined plane would have a greater angle than this one. Oh, wait, no. This one would have the larger angle. My bad. This one would have the shallower angle. Okay? And if we remember, when we're going down an inclined plane, the thing that is causing the net force, which causes the acceleration, is the parallel component of the force of gravity. Okay, so this is really mg sine theta is ma. So the acceleration of these is going to be dependent on g sine theta. Okay, so the larger the theta, the larger the sine function, which means the larger the acceleration. The larger the acceleration, the less time it takes to get down to the bottom of the incline. And if we have less time to get to the bottom of the incline, then that means we are going to land first. Okay, so block 1 is going to land first. So we can say block 1 is on a steeper incline. Okay, but we can't stop there. We have to explain what is the effect of that steeper incline. So, and therefore has a larger acceleration down the incline. Okay. So now we have to talk about the effect of that. What's the effect of the larger acceleration? This larger acceleration means block 1 reaches the bottom of the ramp first. Okay. Off the table, both blocks spend the same amount of time in the air, because I'm trying to be as specific as possible with this time piece. So both blocks spend the same amount of time in the air. So if block 1 reaches the bottom of the ramp first, it will also reach the ground first. So because both of these tables are at the same height, this H is the same. They're going to have the same time in flight off the table. If they were different heights, it would definitely make this problem a lot more complicated because it would just be very difficult to do. So let's check the answer key and see if I got all my points for B2. Let's see, B2. Okay, correct answer is block 1. Awesome, but I don't get any points for that. It's in the explanation. So for indicating that the average speed or velocity on the slide is higher for team 1, I didn't do that. Or that block 1 reaches its maximum speed in less time. Okay, so I didn't necessarily say reaches its maximum speed. I said got to the end of the ramp. Okay, so I would probably give points for that. And then 2, a valid explanation is for why the average speed or velocity is higher for team 1 or why block 1. So we talked about the difference in acceleration. So their example is because the ramp on table 1 is initially steeper, block 1 has a higher average speed while it's on the ramp, so it launches off the table before block 2. So that's their explanation. They went a little different way than I did, but that's okay. That's the thing with physics, is there are often some ways or some different ways to solve the same problem. Okay. All right, so this, as a review, started off as a conservation of energy problem where we have conversion between potential energy and kinetic energy. So we were looking at how did that change in height between the top of the ramp and the bottom of the ramp differ for each of them. And then it turned into a projectile problem where we have motion in the X and in the Y direction. And the Y direction really sets the time of flight for the amount of time we have to travel horizontally in the X direction. So since our Y direction heights were the same, the amount of time was the same, which means the amount of time we had to fly horizontally was the same. So in the first problem, we needed to figure out were the speeds different. And we ended up figuring out that they were. Then in the second problem, we ended up seeing that the speeds at the bottom were the same because of conservation of energy, because all of that same initial potential energy converted to the same amount of kinetic energy at the bottom of the hill. Remember, potential energy is path independent. So it doesn't matter that we take a steeper incline versus a less steep incline. The change in height is the same for both, so the change in velocity is the same for both. Okay, and if our initial heights off the tables are the same, then we're going to have the same horizontal distance. Okay. The differences, though, came up in part B2, where we were looking at which hits the ground first. Block 1 is on a steeper incline, so block 1 has a larger acceleration, and I went through forces why block 1 has a larger acceleration. Okay, so if I'm traveling the same vertical distance but with a steeper angle, that larger acceleration is going to lead to less time that it takes to get down the incline. Less time than it takes to get down the incline, meaning table 1 is going to hit the ground first because the height off of the time off of the table is the same. All right, and that is it for week 2's review problem. See you guys next week.